So hello, today we're going to start chapter 4, which is all about forces. I've accidentally used the word forces a few times already this semester, just because it's a common thing to use. But yeah, we're going to talk about forces, what they mean, what they do, and Newton's laws of motion. A few things about this chapter. First off, this is the longest chapter. We are not going to do practice problems this Friday. We're actually still going to have lecture. I'm going to lecture Monday and Wednesday and Friday and do practice problems of Monday of next week. Monday of next week being March 1st. Then on March 3rd, I will do a review for an exam because on March 5th is your first exam. Like this is Friday, March 3rd. Friday, March 5th is your first exam. General idea is your exam on March 5th will open up at 2 o'clock and will be online. It is made to be a 50-minute exam. The general idea is you have 50 minutes to work on the exam, but it's open for 65 minutes. That's because I'm giving you 15 minutes to upload what you are doing. See, here's the setup. Actually, if you really want to see the setup, if you go on Vanco Hall and go down to the old exams and exam review, you'll find last semester's exam in both PDF form and in the same form that the present exam will be. This can show you not only what type of stuff to expect on the exam, but how the exam is going to actually function. General idea, how the exams look like. Oh, side note, this last semester's exam thing is nothing that is due or going to be collected or anything. It's just there for you. But when you go in, what you'll find is that the exam will be 4 questions long. Each question be on a page of a Vanco Hall thing. And what it is for each one is it'll give a problem and then give an upload thing. And that's what your exam is going to look like. What you're going to do is you're going to do the exam on paper at your desk, take a photo of the work, and upload the entire work, with each problem getting its own page. You know, problem 1, problem 2, and so on. I think part 2 is a GIF. It does. Now, so yeah, that's how it's going to work. If you want practice to how the upload and everything, use last semester's exam. Last semester's exam also exists in PDF form on Vanco Hall right now. But general idea is, as I said, it's made to be a 50-minute exam where you have 65 minutes. I'm giving you an extra 15 minutes just to upload. Make sure you start on time. This is also going to be time management. If you go right up to the last minute doing the exam and don't have time to upload anything, well, if you can't upload everything, I can't see it, and therefore I can't grade it, and therefore it's a 0. So make sure you pay attention to time and get everything uploaded. I will stay online on Zoom during the exam, so if there's any questions, you can ask me. I also ask you do it on your own. If you have identical sheets to someone else and it's very obvious you work together, I will just fail you both and fill an academic warning for academic dishonesty, which have a lot of bad repercussions. Do it on your own. It is open notes though. I recommend don't just have all the notes open, but make yourself like a little cheat sheet type thing, equation sheet, make your life easier. The exam will be only 4 problems long. The first problem will be about free fall from chapter 2. The second problem will be projectile motion from chapter 3. The third problem will be about forces without friction. And the fourth problem will be forces with friction. Um, that's the general setup. That's exactly how it's going to be. Of note, I don't mention chapter 1. That's because chapter 1 kind of sucks, but it will include some stuff from chapter 1. Basically, there will be unit conversions mixed in. There will be at least 1 unit conversion, probably 2 mixed into those problems. I still can't know what date it is. As I said, I've already posted Vanco Hall last semester's exam. What it is on Wednesday, March 3rd, I'm going to go through that exam. As I go through it, I'm going to explain how I grade and some hints and tips. This exam will not be identical to that exam. It will just be the similar type of stuff. I will post the solutions to the last semester's exam right after I go over it. As I said, I recommend doing it for practice. On the 5th. Seriously, I fail. Any questions about the exam before I get started? If you can't make the exam time, make sure you let me know. I might be willing to move some stuff around, but only if you let me know. And yeah, make sure you practice. Okay, since no one's stopping me, I'm assuming no questions, and I will keep going with chapter 4, forces. So, here's the general idea. A force is a vector quantity that produces accelerations. We've talked about how dealing with accelerations in kinematics the last 2 chapters. And it's like, cool, this thing's accelerating. That means it changes velocity. But we haven't said where the hell these accelerations come from. And so that's what we're going to do this chapter. How one creates accelerations. And that's, yeah, forces. General idea is forces is what exists anytime things interact with each other. Now, forces really can be broken into 2 categories, contact forces and non-contact forces. Contact forces is anytime there is physical contact. That if I take this and push it, that's a contact force. If I throw it, I push it against it again, that's a contact force. Contact force is anytime you have something attached to something else, sometimes possibly like attached to a string, like if I swing this around by the string, that is still a contact force. Non-contact forces, there's only 3 of them, and these are forces that do not need contact. A magnet is an example. That if I take these magnets, take this magnet and bring this magnet above, I can make the magnet jump up out of my hand and collect without contact. It pulled it upwards without touching it. There are 3 types of contact forces. Magnets doing that is just one of them. There's also gravity. If you drop something, the earth doesn't have huge hands that show up, grab it and pull it down. It just drops. There goes my magnets. And the third one is electrostatic forces, which one both magnets and electrostatic forces are for physics 2. We're not going to talk about them this class. But in general, yeah, it's anytime things are interacting, whether it's pulling something closer or pushing it away or any sort of interaction. That is what a force is. Now, forces were first defined by Newton's 3 laws that throughout today I'll slowly go through. And the first of Newton's laws is Newton's first law. Kind of makes sense with the name. And Newton's first law is the least useful of Newton's laws, but whatever. And it says, an object will remain at rest or in uniform motion in a straight line unless acted on by an external unbalanced force. What this means is that if the sum of forces on something is 0, its acceleration is 0. That if there is the sum of forces 0, not if there's no force, even though I wrote that there, but if all the forces added up equal 0, there will be no change in direction or speed. If something is moving, it will keep moving at a constant velocity in a straight line. If something is stationary, it'll stay stationary. You can kind of see this here with this dinosaur and I think bowling ball, but it looks more like just a cement thing. That when the ball hits the trampoline, the dinosaur doesn't get pulled down. He just slowly falls with gravity. That, let me wait till this starts again. Right here, he just kind of looks like he floats in the air for a second before he starts slowly falling down. That's because no force acted on him, so he didn't start doing anything until he starts falling due to the force of gravity. Now, it is kind of hard to see on Earth since friction and gravity are kind of ever present. It is much easier to see in space. I think I do have a video though. So let me make this a little smaller. Put it over my dinosaur. So this coat has an accelerometer on it. And when I push on it, when I push on it, the accelerometer reads a lot of force. Can't get to where I was pushing on it because I'm pushing on it. But this is a nearly frictionless track, and you can watch while it's moving before it hits the edge, where it basically had no acceleration, just a tiny, tiny, tiny bit. That's because there was no force acting on it there. And since there was no force, there's no acceleration. That's Newton's first law. Now, to really quantize this idea, we need to introduce another topic that we haven't talked about yet. And that is the idea of inertia. You see, if no force means no acceleration, then some force means some acceleration, just logically. And inertia is the tendency to resist acceleration. What it is if you get something moving, it wants to stay moving. If you have something stopped, it wants to stay stopped. Everything has an intrinsic ability to resist changes in velocity. Everything has an intrinsic ability to say, no, I'm sitting still, fuck you, I'm not going anywhere. Or I'm moving, I'm going to keep moving. And that's inertia. Now, inertia is not normally measured directly. We normally measure something's mass. And mass is simply, what mass is a way to measure inertia. The heavier an object is, the more force you need to change its velocity, because the more inertia it has, because the more mass it has. This ties into the classic thing where someone tries to pull a tablecloth out from under all the dishes and stuff, or in this case, it's going to be a ball. That if I take this ball, place it on this little piece of plastic, and then hit the plastic out from under it, the ball doesn't go flying off to the side. It falls straight down into the cup. That's because the ball has mass. Because it has mass, it's going to resist the acceleration. It's going to resist the force. Now, when this piece of plastic goes flying off to the right, the ball does it because its mass makes it resist it. Its inertia makes it resist it.
So, Professor, isn't part of the tablecloth thing that, like, if you do it slow enough, it doesn't work?
That is true. Part of that, yes, that is true. If you do it slower, it will not work. Same idea that with this guy, if I did it slowly, it would not work. That has to do that if you do it slower, it's giving a better chance for friction to come into play. Basically, because if you do it real fast, we're going to kind of override friction. If you do it slower, you can have friction actually grab on and keep going. That's why.
Okay.
To really explain that, remind me on Friday you asked that question, because Friday is when I'm going to cover friction, and I can do it in a lot more detail once I cover the workings of friction.
Okay, sounds good.
Now, this idea that mass relates force and acceleration brings us to Newton's second law, which is probably the most important of Newton's laws. And Newton's second law says exactly how these quantities are related. And here it is. This right here is the most complicated equation we will use in this class. This is by far, the most complicated equation we do in this class. And what it says is simply F equals ma. But really, it's a little more complicated. It says the sum of forces is mass times acceleration. In this, a few things, because I haven't said explicitly. F stands for force. M stands for mass. First time I've said that. One thing to keep in mind, acceleration is a vector. So is force. So this equation says the sum of forces in any direction is mass times the acceleration. Or the sum of forces in x is mass times acceleration in x. And the sum of forces in y is mass times acceleration in y. This equation really is always two equations. One in x, one in y. And you have to keep that in mind, that it needs to be split into its parts, where you, just like in projectile motion, solve the components independently. And you can use forces to get accelerations in x and accelerations in y. And then if you get the accelerations, use kinematics to solve other things. But that's the general idea. Now, this equation I said is super complicated. There's two reasons for that. One is this vector notation, but the worst one is this. In F equals ma, F will never be, well, very, very, very seldom would be a simple number. This first term, Sure. Why won't you work, computer? My mouse is disappearing. Okay, there we go. This term will almost be its own equation usually, where the equation will come from whatever you are doing in that problem. That is the most complicated part of that equation. You're never very, 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 very seldom where you just plug a number in there, but normally a complicated equation in for that spot because it is the sum of all of the forces that would need to add up. Now, before we get into how to solve that, let's just do a little more breakdown of this. In F equals ma, F once again stands for forces. There are other symbols that are also sometimes used for forces. This is just forces in general. I'll get into the other equations as we go. Forces will use the units of newtons, where a newton uses the symbol capital N, where 1 newton is a kilogram meter per second squared. The American equivalent of a newton is the pound. Well, pound is a unit of force. M stands for mass. Mass once being something, the intrinsic property to resist inertia. Mass is measured in kilograms. And the American unit for mass is the slug. Very, very, very seldomly used. But yes, mass is M in kilograms and F is force in newtons. And basically what this says, Newton second, is that if I apply a force on something like so, it accelerates. How fast it accelerates is based off the sum of forces and the mass. Something heavier accelerates slower. Okay. Now, this sometimes confuses some people because I'm saying pounds measure force and kilograms measure mass. And on this planet, we interchangeably use them. We use, Americans will use pounds and Europeans use kilograms, and we're describing the same thing, how much you weigh. Quick thing. Mass is not the same as weight. Mass is an intrinsic property of something. And your mass is not dependent on gravity. My mass in kilograms sitting here would be the same as my mass in kilograms on the moon. It would be the same as my mass of kilograms floating in space. Mass is always set. However, if you want to know if you're gaining weight or not, and go stand on a bathroom scale, you don't measure your mass, you measure your weight. Now, when you stand on a bathroom scale and the thing moves, it figures out the weight you have. And weight, which uses the symbol lowercase w, is the force due to gravity. The weight of anything will simply be mg, your mass times the acceleration due to gravity. Now, that being said, weight depends on the gravity. So my weight on Earth would be different than the weight on the moon. And in space, my weight would be 0. This is why on Earth we interchangeably use use pounds and kilograms. Because as long as we're not leaving the planet, there's a direct relationship of 9.81 meters per second squared. But mass is an intrinsic property, is the same everywhere. Weight is different depending on what planet you're on. If we ever become a more spacefaring society, we're going to need to do away with weight because it will be different on a different planet. Okay? Now, I'm going to ask you guys a question. This question often messes with people. So I just want to make sure everyone's on the same page. And the question is, if something is moving at a constant velocity, which of the following is true? The net forces acting on an object is 0. There are no forces acting on the object is accelerating, or the object is losing mass. And the poll should have popped up. The majority of you did get it. It means if something's moving at constant velocity, the net force on the object is 0. It doesn't mean there's no force. It means the net force is 0. No force is an option, but like think of it this way. Right now, this thing isn't accelerating. That's not because there's no forces acting on it. Gravity is still acting on it. My hand is holding it up, but the net force is 0. And so if something's moving at a constant velocity, it just means the sum of the forces is 0. That this sigma f is 0. Okay? All right. Let's do a really stupid little example problem that I like to do just because I'm a nerd and I want to make this as complicated to say out loud as possible. Darth Vader uses the Force to knock away a stormtrooper who accidentally turned off the ship's gravity. If the Force causes an acceleration of 20 meters per second squared in the x direction and 15 meters per second squared in the y direction, and the trooper has a mass of 90 kilograms, what is the magnitude and direction of the Force applied using the Force? With the second one capital. Once again, I'm doing this just to be an asshole. Here's the general idea. Using the force, forces are applied, making this guy go wee off that way. And my question is, what is the magnitude and direction of the force? Given an acceleration in x of 20 and an acceleration in y of 15 and a mass of 90 kilograms. If you want to find the force of the force, what you say is, well, there's only one force acting here. There's no gravity, it said. So the only force would just follow by F equals ma. But this really is two equations. This will always be your forces in x is mass times acceleration in x. And your forces in y is mass times acceleration in y. Where you can find each one individually and do some math. But just like last chapter, if you have an x and y component of a vector and you want to know magnitude and direction, anytime you have two components of a vector and want magnitude and direction, you're going to have to go and put them together. And if you know the x and y component of a vector and want to put them together, we'll use Pythagorean theorem for magnitude. X squared plus y squared, and then take the square root. And for direction, it will be the inverse tangent of y over x. Okay? So this is a very...
when we were talking about the sum of the net forces, has that come into play here yet?
It didn't really because it was the only force. I made a comment about knocking off the ship's gravity, so there's no gravity, and we're not having anything else acting on them, so this would be the only force. We'll start doing the sum of forces today, but it doesn't quite come into play yet.
Okay.
Okay, that's Newton's first law and Newton's second law. Newton's third law. Let's go back to this video right here. When I hit this thing and it goes pew off, let's think about what's actually happening. This blue coat is pulling out a stopper that is hitting this black thing. The coat is applying a force to the end cap. But what you see is that the blue coat goes flying. And that by the blue coat pushing the end cap, the blue coat moves. That's Newton's third law. Newton's third law is commonly said as for every action, there's an equal and opposite reaction. And here's the idea. Anytime you apply a force on an object, a force is applied back. If I go and push on my desk, I accelerate backwards. That's because however hard I push on my desk, the desk pushes on me exactly that hard. That's the idea. Every time a force is applied to something, a force of the exact same equal magnitude, but opposite direction, is applied in return. That's Newton's third law. That if you push on an object, it pushes back just as hard. Take something, I hate how often I use guns in my examples, but I'm doing it. This is the idea of a recoil with a gun. If a gun pushes on a bullet, the bullet pushes on the gun. And the magnitude of the force will be exactly the same. They'll just be in opposite directions. Okay? Now, before we can start getting into the type of problems you need to be able to solve, I want to talk about I want to talk about a quick special thing, aka gravity, and then I'll get into the forces in general. Well, that's not true. I'll get into a bunch of special forces, but I'm going to do gravity before I get into how to solve a problem. Because gravity is kind of interesting. We already said that the force due to gravity is something's weight. And so on Earth, the force due to gravity will be mg, your mass times g. But I've never said where that number comes from. Like 2 chapters ago, I'm like, g equals 9.81 meters per second squared. And it's just like, accept that. I never said why it's that number or where it's from. And here's the idea. Any two objects that have mass will have an attractive force between them. Sitting next to me is this table. There was a force pulling me towards that table and pulling the table towards me, equal magnitude because Newton's third law. That's gravity. Earth is pulling me down, that's gravity. Earth is being pulled by the sun, that's gravity. But also, if I hold this here, it's being attracted to my face right now. That's gravity. Gravity is a force between every and any two objects with mass. And that you're sitting in front of your computer, there is a force pulling you towards your computer and your computer towards you. That exists. That is gravity. Now, why that is, that gets into a physics 2 topic, and the bending of space-time is the common theory these days. But the Newtonian theory, which is not a Newtonian theory, but the Newtonian version that explained the equation, says between any two objects with mass, there is a force. That force is capital G, m1, m2 over r squared. Well, capital G is not the same lowercase g we've been dealing with, but capital G is the universal gravitational constant, which has a value of 6.673 times 10 to the negative 11 Newton meter squared per kilogram squared. And anytime you have two things with mass, there will be an attractive force bringing them directly at each other. Now, you can feel gravity due to the Earth, right? I drop it, it falls, gravity. But you never feel gravity between you and like the person next to you because this is such a capital G is such a small number. Gravity is sometimes called the weak force because the fact it is always super weak. If you have two 1 kilogram masses separated by a meter, the force is going to be this. The force of gravity is super, super, super small. Okay. I completely forgot that this video was in here. This is a newer video that I just only recently added, so I always forget about it. Real quick. So here's the thing on gravity.
We're all familiar with gravity as the reason objects fall, but there's much, much more to gravity than that. Gravity is a long-range attractive force between all objects with mass. It's what keeps us from falling off the Earth, it's what keeps the Earth in orbit around the Sun, and it's what caused the Sun itself to form 4.5 billion years ago. It's amazing to think that every massive object attracts every other in the universe. That means that your dog, the Earth, and a black hole in the Andromeda Galaxy 2.5 million light-years away are all gravitationally attracted to you, and you to them. In the 17th century, Isaac Newton discovered that the strength of the gravitational force decreases by the square of the distance between two objects. So if you're twice as far away, gravity is only 1/4 as strong. He also discovered that the strength of gravity is proportional to the mass of the objects in question. The more massive an object, the stronger the gravitational force. That's why we can all feel the Earth pulling on us, but don't really notice the pull of the moon. It's smaller and farther away. The moon's gravity is strong enough to cause the tides, though. And when I said earlier that gravity is an attraction between objects with mass, I lied. I meant objects with energy. Because in addition to massive objects, gravity also attracts light and other massless but energetic particles, so that a photon of light can be bent slightly passing the sun, or trapped completely by a black hole. Now do you understand the gravity of the situation?
That's such an old video for that guy. So that's the general idea. Okay. Now, if you want gravity between you and the planet, when you talk about gravity between two things, you normally go from the center of one thing to the center of the other. So if you want to find the force of gravity between you and the Earth, we'll measure from the center of the Earth to the center of you. But you are much smaller than the Earth. Just telling you. So the distance from the center of Earth to the center of you is approximately the radius of the Earth, which is 6.38 times 10 to the 6 meters. And the mass of the Earth is 5.98 times 10 to the 24th kilograms, just so you know. Knowing G, we can say the force of gravity between you and the Earth. It'll just be G m1 m2 over r squared, where G is the universal gravitational constant, m2 would be the mass of the Earth, r would be the distance between you and the center of the Earth, and m1 would be your mass. This allows some units to cancel out, and you get that the force of gravity between you and the Earth is 9.81 newtons per kilogram times mass. But keep in mind, a newton per kilogram is the same as a meter per second squared. And that's why the force of gravity on Earth is mg, because of the fact that that's just all of those constants put together. And for the most part, when you're doing gravity in these problems, you just say gravity is mg, or you put lowercase w for weight. You won't bother with going and solving this mess. But the force of gravity will be mg as long as we're on Earth. Okay, any questions though?
So just to clarify, this doesn't apply on the x-plane, or it does? When you talk about the gravity between two people.
It could be on any plane. Gravity due to Earth is only in y. But if I put one thing here and one thing, my hand here, there is an attractive force between my hands pulling them together. That's in the x-plane. It's just so small. And it's so small, it's not measurable. So there's a gravity pulling you in every direction. Like, look around your room. Everything you see, there's an attractive force between you and it in that direction. But we ignore it in projectile motion, and we ignore it in basically every problem we're going to do because it's really, 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 really small, unless you got something like the Earth or the
Okay.
sun, or something big and heavy.
Okay.
There isn't a thing big enough that with common machinery, like there isn't a thing big enough on Earth that with common machinery you can see an attractive force of gravity. Some really sensitive things maybe, but it's tiny. Okay, I gotta talk about some special forces, but I'm gonna start getting into solving problems. And if I'm gonna get to solving problems, I need to talk a little bit about how to solve these problems. So I want to introduce you to the idea of a free body diagram. I've said before, when solving mechanics problems, you should always draw a picture. A free body diagram is something you draw when solving a force problem and is crucial. I'll say right now, any problem with forces, I will give points for the free body diagram. But there's always confusion on what a free body diagram is. A lot of people just like to draw the situation, be like, there we go, I made a free body diagram. It's not that. A free body diagram is you draw the object. It just has a box normally, or a dot. And you draw all of the forces acting on it and their direction. Let's say, for example, I got this picture in the upper right of someone pulling on a block. And this block is sitting on the ground. If this block is sitting on the ground, there is a force pulling on it. If it's on Earth, there's gravity. And it's sitting on the ground, which we're going to get into this sitting on the ground thing in a slide or two, but it's sitting on the ground so the ground holds it up. What that does is it gives me this free body diagram. That the free body diagram is you draw all of the forces. And this is how we're going to make our force equations. You just say, yeah, all the forces, what direction they're in, and draw them. The hardest part of force problems is making this drawing and putting all these arrows in the correct direction. Once you have that, these problems will all be very simple and straightforward. But to solve a force problem, you gotta make a free body diagram, or else it's basically impossible. And it was just a way of saying what forces are acting in what direction, and you draw the directions. See, the reason this works is in a standard coordinate system, X is to the right is positive. X to the left is negative. Y up is positive. Y down is negative. And when we say the sum of forces equals ma, what we'll do is we'll use our free body diagram to make this sum of force equation. That if instead of just delta F equals ma, I'm going to make it two equations. Delta F of x equals ma of x. Delta F of y equals ma of y. I said that before. But this first term, this delta F of x, should always be you look at your free body diagram and you add up everything pointing to the right, and from that you subtract everything pointing to the left. Let's say I got a plane flying through the air and I have the free body diagram below. The forces acting on it is lift up, weight down, thrust to the right, drag to the left. I'll look at that and say in my delta F equals ma, that part I put in a red box, that delta F of x will be everything to the right minus everything to the left. And you'll literally look at your picture and say, what points to the right? Cool. What points to the left? Okay. And I'll look at this and say that first bit, delta F of x, is equal to the force of thrust minus the force of drag. You just say every force to the right minus every force to the left. And that's why I said that delta F of x is usually more complicated. Because what you're going to do is you're going to look at it and say, that's not just one term. It's everything to the right minus everything to the left. This was an issue for my Darth Vader question because there was only something to the right. There was nothing to the left. But normally it'd be right minus left. Meanwhile, in y will always be everything up minus everything down. And so you look at it and say, what points up? Lift. What points down? Weight. And so in y, it'll be F lift minus F weight equals MAY. And so that works really nice when you have everything straight along X or Y. Make sense so far? Now, let's say we're going to come back to this problem a little bit, but I got this suit hanging from these two strings. I can say gravity is going to be down, but I can say this force is pulling him up this way, and this force is pulling him up that way, the two ropes, right? And then if I say X is right minus left, and Y is up minus down, if your forces are at right along X or right along Y, how do you do them? Take, for example, in one of the Star Wars prequels, I'm blanking on which one, R2-D2 goes flying around. And how he does that by applying a force F up at some angle while gravity pulls him down. If your free body diagram ever has forces that are straight along X or straight along Y, like this one, it's going up and to the right. What you're going to do is you're going to say, screw that, and make it two forces. If something is up and to the right, you say no. It has a component that is up. It has a component that's to the right. And you'll break it into components just like last chapter, where as long as your angle is measured from the horizontal, X will be the magnitude cosine of the angle, and Y will be the magnitude sine. And what you do is you'll say if something is up and to the right, say nope, two forces, one to the right, one up. If something is down and to the left, say nope, two forces, one is down, one is to the left. And that's what you'll use to make your free body diagram. We'll say this force right here doesn't exist. I'm going to ignore this and say these are my forces. From this, I can make my force equations. I can say at X is right minus left. So it's F thrust cosine theta, and there's nothing to the left, equals MA. In Y is up minus down. So I say F thrust sine theta minus gravity. That's going to be how you solve these. Questions so far? Okay, so I got to talk about a complicated force real fast. And let me check my videos real fast to make sure I didn't skip one. Nope. Okay. So I want to talk about another special force, something called the normal force. So I take this, I drop it. It accelerates downwards. It accelerates downwards because the force of gravity. It accelerates downwards because it has weight. Weight is force of gravity, mg. But if I instead take this and put it on my hand, gravity didn't go away. There's still gravity here. It's sitting on my hand and not moving, even despite the gravity. And since it's not moving, it's not accelerating, that means the sum of forces must be 0. This is called the normal force. The normal force, which is a force, so forces are F, but it's such an important force it gets its own symbol, lowercase n. The normal force is the force exerted by any object and its surface. Anytime two objects touch each other, there is a normal force. And normal force is always perpendicular to the surface. That if I put this on my hand, gravity pushes straight down and the normal force pushes straight up. The normal force is straight up to counteract gravity. Now, there is no equation to solve for normal force. Normal force is whatever it needs to be to match the surface. Because if I put something on a ramp, gravity is still straight down. Gravity is always straight down. Gravity is that way. But normal force is always perpendicular to the surface. My normal force is going to be up at this angle. Now, if you need to solve for the normal force, you're going to have to say the sum of forces. Almost always, if you have a normal force, that means the acceleration in the direction of the normal force is 0. Because if this had an acceleration in y, it would be falling through my hand or shooting off my hand. If it's staying on my hand, even if it's sliding across it, it's not moving up or down. Normally, whatever direction the normal force is, there's no acceleration in that direction. For the diagram I have here, I'd say up minus down equals 0. I'd say normal minus mg equals 0. That means the normal equals mg. But if I instead put this on my hand and then push down with my other hand, I'm applying an extra force downwards. That means the normal force is going to be bigger to compensate. If I take it and kind of half lift it and pull lightly, that means the normal force is going to change to make up for that. The normal force will always change to be whatever it needs to be. And once again, is perpendicular to the surface. If someone is doing a chimney climb, gravity is going to pull them down. But the normal force, there's going to be one here from their feet, and there's going to be one there from their back anytime it is touching. This actually gets back to the idea of a bathroom scale. I said before, bathroom scales read your weight, and that's kind of a lie too. Bathroom scales do not read your weight. They read the normal force they apply to hold you up. That when you step on a scale, let's say you're just on a scale like normal, F equals ma. When you step on a scale, there's nothing happening to you in X. Let's ignore X for now. We'll only look at Y. And what we can say is that if you're just on a bathroom scale standing there, you have no acceleration. And we can say on a bathroom scale, gravity pulls you down. But because you're standing on a scale, you have a normal force holding you up. And what a bathroom scale reads is your normal force. It reads how hard it's pushing you up. Because however hard you push down on the scale, that's how hard the scale pushes you up. And using my up minus down, that means normal force minus mg equals 0. Or normal force equals mg. Scales read your weight because that is your normal force when you're standing on them. But let's say instead, you take your bathroom scale and you go in an elevator, and you put the scale down in the elevator and get on it. And the elevator starts accelerating upwards. If the elevator is accelerating upwards, we can still say there's only forces in y. And we'll still say gravity holds you down and the normal force is up. And your equation is still up minus down, n minus mg. But if you're accelerating upwards, your acceleration isn't 0. You have an acceleration ma. And adding mg to both sides, you'll say your normal force is ma plus mg. And if you're accelerating upwards, the scale won't give you your weight. It'll say you weigh heavier than you think you really do, because it has to have extra to compensate.
Professor, can we go over that one more time? I'm a bit lost.
Okay. So I'm saying that the free body diagram doesn't change. If you're standing on a scale, gravity holds down, normal is up. That's n minus mg. And I'm just saying that if you're accelerating upwards, your acceleration isn't 0. In this first case, If you're just standing on a scale, you're not accelerating. A equals 0. But if you have positive acceleration, you have to include that. Did that help?
Yes, I think so.
I'll actually show it in a second. So
Okay.
hopefully that'll help more. If instead the scale is accelerating downwards, if it's accelerating downwards, you say it has a negative acceleration because down is negative. And if it's a downwards acceleration, the scale will weigh light. It'll say you weigh less than you really do. It'll say you weigh less than you really do because of the fact, once again, the normal force changes to whatever it needs to be. And if shit gets real bad and you go in free fall and the elevator accelerates downwards at a rate g or negative g, you'll get that the normal force is 0, which makes sense. If it's falling downwards, you won't have a normal force anymore. You'll be in free fall. So I got 4 minutes left. I decided to do this. So one summer, I went into Evenden Tower when I thought no one else would be there and tried to ride the elevator while standing on a scale. Fun fact, I had a really hard time getting a moment when no one was coming into the elevator. It was not easy in the end to film this. And let me make sure my audio is still on. Okay, should be able to hear what I say on it. And so this is me just standing on a bathroom scale in an elevator. And you can see I'm pretty fat. I weigh about 230 pounds, which is my weight. But really, that's the normal force the scale reads.
I'm right now standing on the first floor of Evenden in the elevator on a bathroom scale. As you can see, I weigh about 230 pounds, which is my normal force as read by the elevator. If I tell it to go up, we'll have an upwards acceleration, which will mean that the scale gives a higher reading. It will then travel at constant velocity, going back to the 230 pounds. But when we reach the top, we'll have a downwards acceleration as the elevator slows back down, and the number will become smaller.
And that's the idea. That when I'm stationary, 230 pounds. When I'm moving at constant velocity, like I'm just rounding down to make me feel better. When I'm at constant velocity, 230 pounds. But if I'm accelerating upwards, it reads heavy, almost 250. When I'm accelerating downwards, it reads light, about 210. That the normal force changes to be whatever it needs to be. And normal force doesn't have a set value. You have to go and solve for it using your free body diagram, forces up minus forces down. And with that, what is your acceleration and what other forces are there? Yeah, that video took me like 8 takes to make because every time I started doing it, someone would stop the elevator on a different floor to get on, and I'd just be standing there filming my feet on a bathroom scale in the elevator, and they just kind of look at me funny. And I'd be like, eh. That's the idea. The normal force is whatever it needs to be. But you solve for it with F equals ma. Okay? Any questions? So I'm still trying to keep it mostly simple here. Everything was in nice straight lines. We don't really have crazy angles yet. That's going to change next class, where I am going to solve this problem right here, which is going to make it quite a bit more complicated. But we'll get there then. Other than that, have a good day, and I'll talk to you all on Wednesday. Bye.